Partial fraction decomposition is one of the two tools you can use to integrate a rational polynomial function. And this only works if the degree of the denominator is higher than the numerator's degree. So for this one, in the denominator we have a single power term multiplied by a single power term. So if we write the partial fraction decomposition of that, it's going to be something that looks like a over x minus 2 plus b over x plus 1. And now we can cross multiply to get the denominator to look like what we want in the original integral. And here we can just, what we can do, we can actually, since the denominators are equal, we can just make the numerators equal. So it's 3 equal to a times x plus 1 plus b times x minus 2. And from here, to isolate for a and b, you can remove one of them by letting x equal -1. You can isolate for b, so it's just going to be b equals to -1 here. And for a, you can do a similar sort of thing. Just let x equal to 2. That'll cancel out the b because it'll just make that term 0, and you'll get a equal to 1. And from here, you can just plug it back into the original, or the integral, the partial fraction decomposition of it, and so the function just becomes that. And this, solving this integral is pretty simple. It's just, it looks like it's going to be a bunch of ln terms. So it's just going to be ln x minus 2 minus ln x plus 1. For this example, we have an x squared times x squared plus 1. So if you write the partial fraction decomposition of this, it's going to be a over x plus b over x squared. Remember that if you have, it's x squared is basically bracket x bracket squared. So you have to account for that. And cx plus d over x squared plus 1. Again, you can just cross multiply so that you get the following. So then you can let the numerators equal, so it's going to be 1 minus 2x equals ax times x squared plus 1 plus b times x squared plus 1 plus cx plus d all times x squared. And then we can eliminate, we can let x equal to 0 to eliminate all the terms except for b, so we just get b equals 1. And from here we can't really do much else because we can't eliminate the other terms because we got an x squared plus 1. So what we're going to do is we're actually going to group these terms. So first we're going to expand them. So we're going to get ax cubed plus ax plus x squared plus 1 cx cubed plus dx. I just put b back in. So now we're going to group the cubed terms. So it's going to be a plus cx cubed. And then the x squared terms, it looks like it's just going to be 1 plus d. So 1 plus d x squared. And then the x terms is going to be a and just a, and the other one is just 1. So now you have a bunch of linear systems that you can make. So a plus c, well, there's no x cubed terms on the left hand side, so it's just going to be equal to 0. Similar story to 1 plus d, there's no x squared terms, and there's only one x term, it's -2, so we know that a is -2. And because we know a is -2, we can just, from our first equation, deduce that c is equal to 2. And d, well, we can just take the 1 on the other side and make it -1. And then we can plug it back into our original integral, or the partial fraction decomposition that we're trying to solve. So we get -2 over x plus 1 over x squared plus 2x minus 1 over x squared plus 1 dx. And the first one we can get pretty easily, just -2 ln x. The second one is just the integral x to the -2, so you can use power rule on that. And the last integral, we can split it up so that it's 2x over x squared plus 1 minus 1 over x squared plus 1. 2x over x squared plus 1 from our integrating by inspecting video is just going to be ln x squared plus 1, and the last one is just arctan. For this example, to do partial fraction decomposition, we're going to actually have to factor, so the numerator doesn't really matter, but the denominator, we can take out the x squared from the first two terms, and then we can just group the x plus 1's together, so it's just going to be x squared plus 1 times x plus 1, and now you're going to get something that looks similar to the previous example. So we're just going to write the partial fraction decomposition. So we have a x squared plus 1, so that's going to be a cx, or an ax plus b over x squared plus 1. And then we have an x plus 1, so that's just going to be a c over x plus 1. Just going to write it a little bit more compact. And then we can just use cross multiplication and make the denominators common. And then we can isolate for the a, b, and c. So the numerators are going to equal to each other. It's going to be ax plus b times x plus 1 plus c times x squared plus 1. So what we can do is we can actually eliminate the a and b by letting x equal to -1. If we do that, we're just going to be left with c. So on the right hand side, it's going to be -2 times -1 plus 2 equal to, well, this whole term is just going to be 0, and c is going to be 1 plus 1 multiplied with it. And then if you isolate for c, you are going to get -2 times 1 equal to c times 2, so it's just going to be c equal to -1. Now we know that c is equal to -1. We can actually isolate for b by letting ax equal to 0. So we're going to let x equal to 0 now. And so now the left hand side, well, it's just going to be 0 because 2x is 0. That's multiplied by the whole thing. We're going to get ax is 0 times 1, and c is -1, and it's going to be times 1. Isolate for b, and we get 1 is equal to b. So we have our c and our b, and finally we just need a. So we can just let x equal any arbitrary value because we already have our b and c. So let's just let x equal to 1, and we can solve that out. So we're just going to get a plus 1 times 2 minus, or plus minus 1 times 2. And then we just isolate for a. It's going to be 6 plus 2, 2a plus 2. And a is just going to equal to 3. And then we're going to put it back into our partial fractions. So our partial fraction formula from above was ax plus b over x squared plus 1 plus c over x plus 1. Plug in a, b, and c, and we get 3x plus 1, x squared plus 1 minus 1 over x plus 1. And we can integrate this. The right hand side is pretty simple. So 3x over x squared plus 1, we break it up, we get 1 over x squared plus 1 and minus 1 over x plus 1. So the top from our integration by inspection video, we can just write that as 3 over 2 ln x squared plus 1. This is just the integral of arctan, and that one is just going to be ln x plus 1, and you're done. So for this one, you're going to need a handy formula called the difference of cubes formula. So it's when you have some expression a cubed minus b cubed, it's just going to equal to a minus b times a squared plus ab plus b squared. And if you're wondering, the sum of cubes is the same thing, except the minus in a minus b is replaced with a plus, and the plus in the ab is replaced with a minus. So if we can replace our original integral with that using the formula, and then we can do a partial fraction decomposition of that. So we're going to get a x minus 1, so it's going to be a over x minus 1, and then an x squared plus x plus 1 is going to be bx plus c over x squared plus x plus 1. And then we can just cross multiply, so we get a times x squared plus x plus 1 plus bx plus c times dx minus 1. And then the numerators, we can just let them equal to each other. So 3 plus 3x equals to the numerator on the other side. Just going to write it here. And then what we can do is we can let x equal to 1 to eliminate the bx and c terms, so we just get an a, and we just get 6 equal to 3a, so a is just equal to 2. So we have our a, we can plug that back in. So we're going to now let x equal to 0 so that we eliminate the b, the b term, so we're just left with c, and we can plug in a because we already know that it's equal to 2, and here it's just going to be 0 plus c times negative 1, so we can get c, it's just going to equal to negative 1. And now again we can just let x equal to any value we want. We already have our b and a, so let's just let it equal to 2, and then we can just isolate for b, so it's going to be 9 minus 14 plus 1 equal to 2b, and b's equal to negative 2. So then we just plug it into our integral. So the partial fraction decomposition of that is just going to be 2 over x minus 1 plus negative 2x minus 1 x squared plus x plus 1. And the first one, we can just integrate that by inspection. It's going to be 2 ln x minus 1. The second one you can also do by inspection, but I'll do a u sub for this actually. So I'm going to pull out the negative out first, and then what I'm going to do is I'm going to let u equal to x squared plus x plus 1, and du is just going to be 2x plus 1 dx, and you can tell obviously that it's just going to, we're just going to have the integral 1 over u, and then we're just going to get some sort of integral that looks like ln. So we're just going to get a ln u. So plug in the u again, it's going to be x squared plus x plus 1, and therefore the original integral is just going to be 2 times ln x minus 1 absolute value minus ln x squared plus x plus 1 plus c. So for this one, we're going to have to factor the denominator to get our partial fraction decomposition. So the denominator, you can just factor it using a similar technique to how you would factor a quadratic. It works here. So we're just going to have x squared plus 3 times x squared plus 1. And if you do the partial fraction decomposition of that, well, it's a term to the power of 2. So it's just going to be ax plus b over x squared plus 3, and then it's going to be added with cx plus d over x squared plus 1, and then we can just cross multiply, so we get ax plus b times x squared plus 1 plus cx plus d times x squared plus 3, and then we're going to get the common numerator or denominator, and then we can let the numerators equal each other, so it's going to be x squared plus 2x plus 3 equal to 8x plus b times x squared plus 1 plus cx plus d times x squared plus 3. And then from here you can't really isolate a lot, so what we're going to do is we're going to actually expand these. So we're going to get ax cubed plus bx squared plus ax plus b plus cx cubed plus dx squared plus 3cx plus 3d. And here you can group the x cubed terms together, and that's just a and c, and then the x squared terms together, which is b and d, and then the x terms, which is a and 3c, so it's going to be a plus 3c times x, and then the x to the 0 terms together, so it's b and 3d. And then we can make our linear systems here, so we get x cubed. There's no x cubed on the left side, so it's just going to be a plus c equal to 0. And x squared term, well, there is one x squared, it's just 1x squared, so it's going to be equal to 1. And then the x terms, well, it's just 2x, so it's going to be equal to 2. And then finally, the x to the 0 terms, there's 3 in the left-hand side. And here, I'm just going to do some substitution. So I'm going to make a equal to negative c, and then I can put that in here to get the value of c. Value of c is going to be 1 if we work that out. And then again, I'm going to do the similar sort of thing. I'm going to isolate b for d, so it's going to be b equals 1 minus d. And since we have c equal 1, we can actually write, we can actually solve for a as well. Since we know a is equal to negative c, a is just going to be negative 1. And since b equals 1 minus d, we can just put that into this formula, formula 4, to get the value of d, which is equal to 1. And since we know the value of d, we also know the value of b, which is equal to 0. So then we can just plug it back into our partial fraction formula. And our partial fractional formula from above was ax plus b over x squared plus 3 plus cx plus d over x squared plus 1. So we plug it in, it's going to be a is equal to, so it's going to be x over x squared plus 3, and actually a is equal to negative 1, so it's that. And then c was 1, so it's just going to be x, and d was 1, so it's going to be plus 1. And our integral is going to look like that. So let's actually split it up. So it's going to be negative x over x squared plus 3 plus x over x squared plus 1 plus 1 over x squared plus 1. So now we can integrate all of these by inspection. The first one is just going to be negative half ln x squared plus 3. The second one is just half ln x squared plus 1. And the last one is just going to be arctan. Now in the denominator we have some x squared plus 1 term to the power of 2. So here we're going to have to do ax plus b over the x squared plus 1 term, but then we're going to have another term of the same thing but to the power of 2. So cx plus d over x squared plus 1 to the power of 2. And then we're just going to do our common denominator cross multiplication shenanigans, and we're going to let the numerators equal each other. So x squared plus x plus 1 is going to equal to ax plus b times x squared plus 1 plus cx plus d. Now we can expand, so we get ax cubed plus bx, or ax plus bx squared plus b plus cx plus d. And then we can group the different terms together. Well, for a x cubed, there's only one x cubed term. It's just going to be ax cubed. For the x squared terms, there's only one. It's x squared. And for the x terms, there's only a and c. And then for the x to the 0, there's b and d. So now we can create our linear equations. So a is just going to equal to 0 because there's no x cubed terms on the left, and b is going to equal to 1 because there's only one x squared on the left. And then we have other equations, a plus c equal 1 and b plus d equal 1. Well, a plus c equal 1, well, we already know the value of a, it's just 0, so c equals 1. And b plus d equaling to 1, well, we already know the value of b, so we can just get d equals to 0. So now we know all of our values. We can plug it into the formula, which is ax plus b over x squared plus 1 plus cx plus d over x squared plus 1 squared. And we're just going to get 1 over x squared plus 1 rather, plus x over x squared plus 1 squared. So the first one we know is just going to be arctan. And the second one, we can do a u sub to solve this. So we're going to let u equal to x squared plus 1, and du is just going to be 2x dx. And then isolate for x. So then our original integral is going to look like 1 over u squared times du equaling to our integral. So then we can, let me bring this down. We can take out the half, and we're going to get u to the negative 2. We can easily integrate that using power rule, and then we can plug in the u back, so we get that. So our original integral is going to be arctan x minus 1 over 2x squared plus 1 plus c. Final example I want to do is a question that I've seen in my Calc 2 midterm. So these two questions are similar. So the first one, e to the x over e to the 2x plus 3ex plus 2. We can do a u sub first, so that we end up getting du over u squared plus 3u plus 2. And then we get something that looks like something that we can use partial fraction decompositions for. So we're just going to get your a over u plus 1 plus b over u plus 2, and then we can do the cross multiplication, common denominator stuff, and let that equal to the numerator. I'm just going to skip a few steps here. So now we can isolate for the variables like we've done before. Here it's nothing new, we're just doing the same thing we've done basically in the first example. We can isolate for a and b, so we get a equals to 1 and b equals to -1, and then we can put that back into our original integral. So it's going to be 1 over u plus 1 plus -1 over u plus 2, and we can integrate that by inspection. It's just going to be ln u plus 1 minus ln u plus 2. And like I said, 2 is exact same steps, just with sin x, and you'll get the exact same partial fraction decomposition. Everything's the same, it's just with sin x. In a subsequent video, I'll be covering the other technique, which is what you do if the numerator's degree is greater than or equal to the denominator's degree. There you'd have to use long division.